Welcome to G Fun Facts Online. Today we are diving deep into what might be the single most high-stakes gamble in the history of computer science. We are talking about a technology that has been promised for decades, hyped to the moon, and has even seen major scientific retractions that shook the confidence of the physics world. We are talking about Microsoft's lonely, expensive, and potentially revolutionary bet on a ghost particle called the Majorana fermion. This is the story of the Majorana 1 chip, and why the future of the entire quantum computing industry might depend on whether a tiny, fingernail-sized chip can tie a knot in the fabric of quantum mechanics. Let's get right into it. To understand why this chip matters, we first have to look at the wall the rest of the industry has hit. It is called the error paradox. For years, we have heard that quantum computers will solve problems that classical supercomputers cannot touch, designing new drugs, cracking encryption, reversing climate change. And theoretically, that is true. But in reality, building these machines is a nightmare. The fundamental unit of quantum information, the qubit, is incredibly fragile. If you look at a standard qubit, like the ones used by Google or IBM, it is terrified of its environment. A slight vibration, a tiny change in temperature, or a stray magnetic field causes the qubit to decohere. It loses its quantum state, and your calculation turns into garbage. The industry's solution to this is something called quantum error correction. It is a brute force approach. You take one single logical qubit, the one that actually does the math, and you surround it with thousands of physical qubits just to check for errors and correct them. It is redundancy on a massive scale. And this creates a vicious cycle. To get a useful machine, you need millions of physical qubits. But adding more qubits adds more noise and more control wiring, which requires even more error correction. It is a scaling trap. If you tried to build a useful quantum computer using today's standard methods, you would likely need a device the size of a football field, consuming the energy of a small city, just to keep the error correction running. This is the dead end that Microsoft saw coming years ago. While everyone else rushed to build noisy, imperfect qubits, Microsoft decided to take a completely different path. They decided to pursue topological quantum computing. The idea here is elegant, but incredibly difficult. Instead of fighting errors with thousands of backup qubits, why not build a qubit that is immune to errors by its very nature? This brings us to the ghost from 1937, Ettore Majorana. Majorana was an Italian physicist, a genius on the level of Einstein, who disappeared mysteriously on a boat trip to Palermo. Before he vanished, he theorized a particle that is its own antiparticle. For 80 years, this was just math. But in the world of condensed matter physics, under extremely specific conditions, electrons can dance together to simulate this particle. Microsoft's entire strategy rests on trapping these quasi-particles, known as Majorana Zero Modes, on a chip. This is the concept of the topological qubit. To explain how it works, we need to talk about donuts and coffee cups. In topology, a branch of mathematics, a donut and a coffee cup are the same thing because they both have exactly one hole. You can stretch the donut into the shape of a cup, but as long as you don't cut it, that hole remains. The hole is a robust feature, it is protected. Microsoft's chip uses this same principle. They encode quantum information not in a single electron, but non-locally, shared between two separated Majorana modes at opposite ends of a nanowire. Imagine a piece of string with a knot in it. You can shake the string, twist it, or vibrate it, essentially representing thermal noise or interference. But the knot stays there. The only way to get rid of the knot is to cut the string or untie the ends. Local noise cannot destroy the information because the information is stored globally across the wire. This is called topological protection. This changes the physics of how we compute. In standard quantum computers, you fire microwave pulses at qubits to change their state. It is an analog process, and it is prone to errors. If your pulse is just a fraction of a percent off, the calculation drifts. But with Majorana particles, you use a process called braiding. You physically move the Majorana modes around each other on the chip, tying their timelines into knots. The calculation is the knot, and here is the magic. The result depends only on whether you completed the braid or not. Did particle A go around particle B, yes or no? It doesn't matter if it wiggled along the way. This makes the computation digital. It is a massive leap in stability. So what is this new device, the Majorana 1? Microsoft claims to have engineered a new state of matter to make this happen, something they call a topoconductor. It is a hybrid material stack. They take a semiconductor nanowire made of indium arsenide and coat it with a superconductor, aluminum. When cooled to near absolute zero, the superconductivity leaks into the semiconductor, and combined with a magnetic field, it forces the electrons into a topological phase, creating those elusive Majorana modes at the ends of the wire. The chip itself doesn't look like a standard processor. It looks like a series of hashtags or ladders. These geometric patterns allow the system to move the quasi-particles around using simple voltage gates, like a sliding tile puzzle. This is another huge advantage. Competitors need racks of expensive, heat-generating microwave equipment to control their qubits. Microsoft just needs voltage. It is simpler, smaller, and easier to scale. But we have to address the elephant in the room. This technology has a controversial history. In 2018, a Microsoft-led team published a paper in Nature claiming they had found the particle. It was a massive moment, but the physics community, specifically researchers like Sergei Frolov, started finding holes in the data. It turned out the team had cherry-picked their results, excluding data that didn't fit the conclusion. The paper was retracted in 2021. It was a humiliating blow, and led many to believe that topological quantum computing was a fantasy. That is why the release of Majorana 1 is so significant. Microsoft is trying to prove they have moved past the bad science. They have introduced a rigorous new standard called the topological gap protocol to certify their devices. They claim the new chip passes this protocol with flying colors. However, skeptics are still demanding to see the actual braiding operation. They are essentially saying, "Don't show us graphs, show us a computation." Microsoft says that is exactly what Majorana 1 is built to do. Beyond the hardware, Microsoft is building a massive software ecosystem called Azure Quantum Elements. They realize that a quantum computer won't work alone. It will be part of a hybrid loop. You have massive classical supercomputers, you have AI models trained on physics data, and then you have the quantum machine. They call this the co-pilot for science. The idea is that an AI proposes a new molecule for a drug or a material. The classical computer screens it, and the quantum computer handles the hardest part of the calculation, the complex electron interactions that classical computers simply cannot simulate. This brings us to the future. If, and it is a big if, the Majorana 1 chip works and scales as Microsoft predicts, what can we actually do with it? The applications are staggering because they deal with simulating nature itself. The first holy grail is nitrogen fixation. Right now, making fertilizer consumes about 2% of the world's energy supply because we have to use high heat and pressure to break nitrogen bonds. But bacteria do it in the soil at room temperature using an enzyme called nitrogenase. We can't simulate this enzyme on classical computers because the quantum mechanics are too complex. A topological quantum computer could map this process, potentially teaching us how to make fertilizer with zero carbon emissions. Then there is carbon capture. We need new materials that can suck CO2 out of the air efficiently. A quantum simulator could sift through millions of molecular structures to find the perfect sponge for carbon. We are also looking at self-healing materials, concrete that fixes its own cracks, plastics that regenerate. These are engineering problems that are currently stuck in the trial and error phase, because we can't simulate the quantum behavior of the molecules. And of course, there is encryption. A 1,000,000-qubit machine would break RSA encryption, the standard that protects the internet. But it would also be the tool used to design new, quantum-proof security. Microsoft's roadmap is aggressive. They believe that because their qubits are smaller and require less error correction, imagine 10 physical qubits per logical qubit instead of 10,000. They can fit 1,000,000 qubits on a single wafer-sized chip. That is their moonshot. While competitors are struggling to wire up 1,000 qubits, Microsoft is designing lithography masks for 1,000,000. It is the difference between building vacuum tubes and building the transistor. So here is the conclusion. The Majorana 1 is the gamble of the century. Microsoft is largely alone on this path. Google, IBM, and Amazon have chosen safer brute force routes. If the Majorana chip fails, if the physics turns out to be impossible to control, Microsoft will have wasted billions in years of research. But if it works, the error paradox dissolves. The barriers to scaling vanish. We would jump from the noisy, experimental era of quantum computing straight into the era of utility. We are watching the turn of a card. The stakes are nothing less than the future of computation. For now, the Majorana is still Schrödinger's cat, both a revolutionary breakthrough and a theoretical ghost, but the box is about to open. Thanks for listening to G Fun Facts Online.